Hello, my name is Kelly Zhou, and this is Lab 5, Magnetic Braking with Faraday's Law. So the objective of this lab is to observe Faraday's Law through a magnet falling through a tube of aluminum foil and to model this computationally. The physics concepts used are Faraday's Law, which is to calculate the change in magnetic flux to find the current in each ring on the tube, Biot-Savart law to calculate the force exerted on each current-carrying ring, and Newton's third law to calculate the force exerted on the magnet by the current-carrying tube. We are using a roll of aluminum foil in this lab instead of a ferrous tube because aluminum foil is not magnetic. So from the result of this lab, the magnet took 1.232 seconds in real life and 1.175 seconds in the computational model to fall through the tube. So here is our experimental data. So we took a tube of aluminum foil and dropped a magnet through it and found the time it took for the magnet to travel through the tube. So the average time was 1.232 seconds. We observed that the magnet fell through the tube of aluminum foil slower than it would have in free space. Here are some of the different measurements needed for the computational model. The magnetic moment mu is 5.53 amps meters squared, and this was calculated from a previous lab. Here's the code for our computational model. So, as you can see, here we are initializing our velocity versus time graph, and we're also setting up the parameters for the tube of aluminum foil. In this portion of the code, we are creating the tube of aluminum foil and we're creating the bar magnet using our measurements from earlier. Here we're setting up the initial conditions and we're also creating the functions that will calculate the magnetic field and the change in flux over time of each ring due to the falling magnet. Here we're actually simulating the magnet falling through the tube. And at each step, we are calculating the gravitational force and we're calculating the magnetic force on the magnet. In order to calculate the magnetic force, we're computing the change in flux over time and using that to help us calculate the current in the ring. We're also calculating the magnetic field and calculating the magnetic force. After we found the magnetic force, we're calculating the net force by adding the gravitational force to the magnetic force. And then in step 8, we are updating the bar magnet's velocity and the bar magnet's position. Here's our result from our code. As you can see from the photos, this is simulating the bar magnet falling through the tube at the beginning of the simulation and at the end of the simulation. So from the velocity versus time graph, we see a huge dip in the velocity at the beginning, and this is because the bar magnet is still falling in free space and gaining velocity before it hits the tube of aluminum foil. As you can see, as the bar magnet is inside the tube, the velocity plateaus off, and this is because the net force in the tube is roughly around 0, and so the velocity would be the same throughout. Then you can see the velocity then dips again at the end of the graph, and this is because it has exited the tube and is yet again gaining speed. So the time in the tube was 1.175 seconds, which is very similar to our experimental data of 1.232 seconds. So what if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the current would be larger and the magnetic force would be greater, so the magnet would fall slower through the tube. What if holes or slots were cut into the tube? How would this affect the ring current in your model? I said that there would be less induced magnetic fields, so the magnetic force would decrease and the magnet would fall faster.